Apple presents CoreML to developers as a frictionless, three-line Swift API. You pass in data, and you get a prediction. But to understand how it processes data, you have to look past the elegant software interface, down into the intricate geometry of the physical hardware. Beneath that abstraction layer, CoreML operates as a ruthless black box hardware scheduler. The origin of these strict routing rules dates back to the A11 Bionic chip, the first to feature a dedicated Apple neural engine. There is a pervasive misconception among iOS developers regarding the .ml package file format. It is often treated as a pre-optimized executable, but the reality is more volatile. Translating a PyTorch model into an Apple container format mathematically guarantees absolutely nothing about where or how efficiently that code will execute on the device. Treating CoreML like a standard cloud inference runtime, throwing abstract math at it and expecting a server to scale, ignores the physical thermal limits of a passively cooled smartphone. To deploy generative AI at the edge without destroying battery life and device performance, you must master the exact physical silicon constraints that Apple's framework aggressively attempts to hide. Apple's Edge AI performance is built on their specific memory architecture, prioritizing hardware-level data flow over unique mathematical algorithms. In a traditional x86 server or desktop environment, executing a model means painstakingly copying massive datasets from the system's main RAM across a physical PCIe bus to reach an isolated discrete GPU. Apple bypasses this bottleneck with a unified memory architecture. The CPU, GPU, and neural engine share one central memory pool, enabling zero-copy inference. The CPU pre-processes an image, and the neural engine immediately reads that address without data duplication. On high-end Apple silicon, this shared architecture achieves 546 gigabytes per second of memory bandwidth, rivaling dedicated workstation GPUs without melting the laptop chassis. CoreML acts as a strict traffic controller, managing access to this shared memory pool to prevent thermal overload. The intelligence inside this black box belongs to the ahead-of-time compiler. When an application launches, this compiler generates an ML compute plan. This plan maps out exactly where the math will happen. This schematic of the M1 chip shows the available hardware destinations: the 8-core CPU, the 8-core GPU, and the highly specialized 16-core neural engine. The compiler dissects a neural network layer by layer. It evaluates each mathematical operation and attempts to match it to low-level hardware primitives, like basic neural network subroutines for the CPU or metal performance shaders for the GPU. To reach the ultra-efficient neural engine, data must follow strict geometric rules, requiring a rigid, four-dimensional, channels-first tensor layout. If the compiler encounters an unsupported operation, it silently rejects the workload, forcing a fallback to the GPU or CPU. Dynamic sequence lengths, the fluid input sizes required to generate text in large language models, frequently trigger this exact hardware rejection. The physical consequences of this silent fallback are immediate. Hitting the GPU for a task meant for the neural engine causes aggressive thermal throttling and rapid battery drain. If you test your app exclusively on an Xcode simulator running on a desktop chip, you will never notice this failure. Desktop machines simply do not possess the same strict thermal watchdogs of an iPhone. CoreML intentionally hides this routing logic. It trades transparency for system stability, prioritizing device uptime, even if it quietly destroys your latency targets. This opacity leads directly to the quantization trap. Compressing a model's file size down to 4 bits does not automatically guarantee a low active memory footprint during execution. To maintain mathematical accuracy, CoreML frequently decompresses those weights back into 16-bit precision inside the active memory buffers. This expansion collides with the most dangerous hidden hardware rule of the Apple neural engine, the 64-byte boundary padding requirement. The hardware memory controller demands precise alignment. If you feed it a non-aligned one-dimensional tensor, the hardware forcibly injects empty data until hitting a 64-byte boundary. This invisible padding bloats a small memory block to 64 times its intended size. A compressed 300 megabyte model on disk can expand to allocate over 1.6 gigabytes of active RAM, rapidly exhausting the 2 gigabyte safety limit enforced on a standard iPhone. Once that threshold is breached, the iOS JetSAM watchdog intervenes, executing a silent, uncatchable termination of the application. Failing to format your abstract math to fit Apple's exact physical silicon rules turns CoreML from a hardware accelerator into a system crash. The explosion of autoregressive generative AI broke CoreML's legacy architecture, which was designed for static, single-pass classification. Generating text requires continuous loops. Recalculating an entire attention mechanism from scratch for every single new word is a massive computational waste. Apple addressed this with a new structural class called ML State. It allows the framework to maintain a persistent memory cache of key and value tensors across continuous inference loops. By caching these states, the hardware only needs to calculate the mathematical delta for the newest input token, keeping latency low. Apple also introduced multi-function models. This solves the problem of deploying multiple specialized AI features without duplicating massive base model weights. Instead of loading multiple complete models into memory, an application can dynamically swap tiny, specialized LoRa adapters in real time over a single stationary foundation model. CoreML survives the generative era entirely through this elaborate caching and deduplication, dodging the fatal cost of constant memory reallocation. This chart shows the decision matrix engineering leads face when deploying edge AI. It categorizes runtimes like ONNX, TensorFlow Lite, and CoreML across axes of cross-platform portability versus Apple thermal optimization. CoreML provides absolute data privacy and unmatched thermal efficiency on an iPhone. But that efficiency is paid for entirely with severe vendor lock-in and opaque execution logic. The engineering rule is clear. Use Onyx or Executorch if you demand cross-platform parity. But if battery survival on an iPhone is mandatory, you must submit to CoreML. Even so, the framework has deep systemic limitations. It remains structurally incapable of managing continuous on-device training or fluid, agentic routing across different models. These exact bottlenecks are now driving Apple to transition away from this legacy framework. Anticipated for the iOS 27 lifecycle, a new Core AI layer is expected to bridge the gap between local silicon constraints and Apple's server-side private cloud compute. The software abstraction layer is just a temporary convenience.